This will be the outline for this today's talk. So initially I try to introduce the material, and again this CVD is basically a method to develop the material, because there are different methods, as you know, to realize a complete semiconductor device. So among them, so CVD is one of the techniques. So then we'll see these three case studies considering the different materials. So again, for all these materials we need CVD, and we'll see how this CVD plays an important role and what type of materials we can develop using this CVD. So initially we'll start with CVD for silicon, that is widely used this technology, because most of the electronic device we are using at present, this is made of silicon. Followed by that we'll discuss this CVD for compound semiconductor, so that is gallium nitride or gallium arsenide like 3-5 semiconductor, and then we'll discuss more recently emerging this 3 oxide, that is gallium oxide like semiconductor, and how we can use this CVD. So again, you can quickly read that this CVD is having different term or name, like in case of silicon it is generally called PCVD. Then for 3-5 like gallium nitride or gallium arsenide, it takes the name of MOCVD, and finally for 3 oxide it is called as LPCVD. So we'll discuss how this name we are giving, and how it is helping us to develop that particular material. So finally we will conclude. So again, just to give an overview, to realize any electronic device, as we know, so there are broadly 4 categories. So anyway, so this electronic system, like you can consider this laptop, this projector, anyone. So broadly it is an electronic system. If you just open this electronic system, you will find a lot of circuits, and those circuits, again, if you finally dig into this, so you will find out a lot of passive and active devices. So, and finally all this material, all these devices, circuit, everything is made of some material. So today again, our focus is how to develop this material considering this semiconductor technology. So again, just to recapitulate this quickly, what is this semiconductor material? Again, so this is the silicon and germanium. These are the widely known this elemental semiconductor. And then along with this elemental semiconductor silicon germanium, we have this compound semiconductor, where we have 2 different atoms coming from either from group 3, that is gallium or aluminum or indium, or this group 5 in our this periodic table. So then again, if we look at the history, the evolution of material, how different semiconductor materials have evolved. So there we can see the journey started with the germanium in the year 1955. Although this is considering the power application, but it happens with the typical for all other applications like digital logic or analog application as well. So if you see this material evolution, so initially it started with germanium. Then there was this silicon. So after that, so people moved to gallium arsenide, then silicon carbide around 1990, then around 2000 this gallium nitride. Again, this gallium nitride Nobel Prize also given to 3 scientists in the year 2014. So the after gallium nitride, considering the power application, this aluminum nitride, gallium oxide, like these materials are coming. So again, what is the reason behind this material evolution? The mainly reason is that, again, from industry point of view, or again from research point of view as well. So the 2 main factors which drives this semiconductor, this evolution, are the performance of devices, and the cost. So performance should be as high as possible. So again, at lower cost. So now people people move to this all compound semiconductor like gallium arsenide, then silicon carbide, gallium nitride, or this 3 oxide like gallium oxide. So just to have or just to achieve better performance, considering this here, this is considering the power application. Power application requirement is high voltage as well as high frequency requirement. Now, if you want a very high voltage and high frequency requirement, your silicon material cannot provide you that advantage. So that is why people move to all these other semiconductor. And now we will try to map our this CVD technology, how it is helping us to build our devices from this different type of material, elemental semiconductor like silicon, and to our compound semiconductor like gallium arsenide, gallium nitride, even gallium oxide. So then again we know, so considering the type of crystallinity, we have three categories of material. So this is again very basic concept. There are three categories: crystalline, like all the atoms are properly arranged in a semiconductor material. Then we have this polycrystalline. So there are different grain. So there are order, but it is not perfect. So there are some grain boundaries. So then after that we have amorphous. So again, I think you know that although mostly in semiconductor technology development we focus on crystalline material, so to make the active part of the device. But all the material, that means you need crystalline material, you need polycrystalline material, as well as you need amorphous material. So if you just quickly see this is a typical MOS structure. So here you can see this polysilicon, it is the gate metal, or again gate metal can be replaced with this polysilicon. So here we are using some material which is polycrystalline, and then below this we have oxide, silicon dioxide. It has no crystallinity, that is it is amorphous material, and below we have this silicon, that is crystalline. So considering crystallinity, we need all type of material. That means when we look for some method like CVD or any other technique, we need to develop material considering all type of crystallinity. We need crystalline material, polycrystalline material, as well as amorphous. So now again, considering that this electrical conductivity also, it is not that we will only focus on semiconductor or semiconductivity where our conductivity or resistivity lies in between two limits. So we can quickly see this is a small portion of our integrated circuit. So here if you quickly see we have this metal layers. So again, these metal layers are all through the way connected to our active device using different vias, and these metals having your resistivity around 10 to the power minus 6 ohm centimeter. So now, if we see this semiconductor, it has some resistivity in between your metal and insulator that we know, which we can also modulate. That is why this active device portion is made of semiconducting material. And then we have also insulator, where the resistivity is 10 to the power 16 ohm centimeter. And followed by that, we also use plastic or PVC like material to encapsulate all these ICs, which has resistivity of the order of 10 to the power 18 ohm centimeter. Now if you see the order of difference in terms of conductivity, it is 10 to the power 24 order of difference from metal to plastic or that PVC that we use to encapsulate this IC. That means when we develop the semiconductor in industry, we need wide variety of material development considering the electrical conductivity. So this is the take-home message from this particular slide. Now how to develop? So this is all about semiconductor brief introduction, which already you know. So then how to develop this material? So when it comes to developing this material, so we have broadly two techniques. So this is the material development. So one is this bulk crystal growth. So bulk crystal growth means we'll grow the substrate. So again, there are different techniques like Joe-Chalsky floating zone Bridgman technique, where we are making this kind of ignore, and after this soil we are getting this CD like this round shaped substrate. So this is again called bulk crystal growth. And again, another type of this material development we need to do, so that is called again from the previous discussion also you probably know that there are another material development for thin film. So thin film can be in two ways broadly. So one is CVD, chemical vapor deposition, and another one is the PVD, so physical vapor deposition. So both can be either epitaxial, non-epitaxial. So here also you can get epitaxy or non-epitaxy. What is this epitaxy? Just to elaborate, so epitaxy means this is probably a Latin word. Epi means above, taxi means ordered manner. So this is again, I just as I mentioned. So this is again, what is this picture? So this is a part of your gallium nitride device or or transistor. So here this material is starting from the silicon substrate. After that we have this aluminum nitride like nucleation layer. NL stands for nucleation layer. So after that we have this alloy, ternary alloy. Then we have this gallium nitride, and our mainly the electron flows in this transistor from within this layer, that is the gallium nitride. But we need all the other material just to get the better quality gallium nitride. Again, you know that substrate we need to hold. So this is a platform. So again, all the drama of our electron will happen in this active part of your device, but we need to provide some platform. So that will be provided by this substrate. Here in case of gallium nitride devices, it is silicon substrate. So one is it is providing the platform. Another very important role of this substrate is to emit the heat, because you know when this electron will flow through the gallium nitride layer, there will be lot of heat produced. So that heat also you need to dissipate efficiently, otherwise this whole device can burn. So the thermal conductivity of this substrate is also another important thing to look at. So now, but this is considering this compound semiconductor development. But in case of silicon, you know, I will show you shortly that in case of silicon, mostly we take the silicon substrate, then we implant different dopants, and then we etch and we process, and we do lithography, then we get the typical CMOS devices. We don't have as such this thin film or this crystalline layer deposition, but we need CVD also. We will shortly show that. So this is overall how this semiconductor material development are categorized into broad category. So now again further, if we see this thin film development, that is CVD and PVD. So for silicon technology, so we are mostly developing amorphous layer and polycrystalline layer using this thin film development. And here the typical CVD technique we used in case of silicon technology is low pressure CVD, atmospheric pressure CVD, and plasma enhanced CVD. And similarly, the physical vapor deposition we use in case of silicon technology to develop either amorphous or polycrystalline material. So these are the your method, sputtering as well as thermal or thermal evaporator or tube evaporator. Now when it comes to this compound semiconductor technology development, that means where we have two different type of atoms and this gallium nitride or gallium oxide like this compound semiconductor. So there, in case of CVD, we use metal organic chemical vapor deposition like technique, or low pressure CVD or like technique. And here our objective is mostly to develop the crystalline layer. So see how this different type of material we are developing using different CVD as well as PVD technique. And again, when developing this compound semiconductor, so in case of physical vapor deposition or PVD, we have this MOCVD like MV like technique, that is molecular beam epitaxy. So now in the first case study, let us quickly see how we are using this CVD in case of silicon CMOS. So again, overall our objective is to get the final encapsulated CMOS inverter, let's say, starting from this ignot. So this is a 300 millimeter or 12-inch ignot, and these are the different wafers, this round shape. So from here, our objective is to get this kind of packaged CMOS inverter IC. Now, how we are developing this and how we are getting this kind of IC starting from this silicon wafer. And this silicon wafer we are developing using this bulk growth that we elaborated in just previous slide. So let's see what are the different steps involved in realizing this IC starting from this wafer. So the first step, again, here we are taking P-type silicon. So this is not intrinsic silicon. Here the silicon is boron, either boron dope. So then this is a P-type silicon. Then after that we will oxidize this P-type silicon. We will simply, that means we will deposit silicon dioxide essentially on the substrate. Then we will do the lithography. We will open a window in the silicon dioxide layer, and then we will do after etching. So following that etching or opening the window in the silicon dioxide, we will deposit arsenic. So why we are depositing arsenic? To get the N-type material, because overall our objective is to get, again we will show just how to get a diode in N plus P diode. So here this is the p-type silicon. If we implant arsenic, so then this portion of our silicon will become n-type. So our type of semiconductor, like the type of your silicon is changing from p-type, where our magnetic carriers were holes, now it is becoming the electron. So in this portion we have this n-type semiconductor after implanting arsenic and after annealing and diffusing. So we'll get this portion of semiconductor converted to n-type. So after once again we'll deposit this aluminum by sputtering PVD technique, and finally once again we'll do the lithography, and after using this after doing this lithography we'll open another window. So this is the another window. Here we have etched out this metal aluminum portion. So again we'll deposit this silicon nitride, but this silicon nitride is a CVD deposited silicon nitride, which we are doing here at our center also. So then after again doing this lithography and etching, we'll open another window within this silicon nitride, and then we'll do this photoresist deposition, so just to protect this front side of our device, and we'll do the back side milling. So back side milling means this side we'll try to etch out, so this side will mill. So following that, we'll deposit this gold at the back side after this back side milling. So now we will again remove the photoresist from the top and see if we connect this two wire. So here we have this N-type connection. So this wire all the way it is connected to N side of our diode, and here in the back side through this gold contact it is connected to P side. So here after almost 13 steps we are getting this IC or this CMOS like this thing realized from starting from the simple substrate. But here where is the role of our CVD, which is the topic today. So here to deposit the silicon nitride we need this CVD like technique. So what is this CVD? Let's see. So then CVD is broadly here when depositing, let's say, silicon nitride for the silicon CMOS technology. So here we are basically using two gas 1 and gas 2. So this gas 1 here in case of silicon nitride, one is silane, another one is the ammonia. So they are coming from these two different source, and they are then reacting. After this reaction, so here is the difference between PVD and the CVD. Here we have some chemical reaction. So after this reaction, that some atoms will be deposited on the wafer, so that is silicon nitride, and the residue will go out after this deposition of this atoms. So all three CVD process is consist of typically these three steps. So initially there will be gas transport, different gas will come to your chamber, and then there will be some chemical reaction, and then after this reaction with these two gases, so here in the bracket G stands for gas, and here in the brackets A stands for solid. So you can see after chemical reaction between this gas A, B, so then we will get this solid formation on the substrate. So and then this another residue or this byproduct we need to remove from the chamber. So this is the overall CVD process what is happening in case of this is irrespective of any CVD, but again for silicon nitride, here this is silane, this is ammonia, here we are getting silicon nitride and some byproduct is coming out. So again, what are the advantages of CVD? So when we are using this CVD in silicon technology, so now the advantages are there are no crucible interaction. So what is this crucible interaction? So typically in case of PVD deposition we are using some container to keep our this material. So again in case of MB like PVD also we are using some container. So there might be some chemical reaction which may degrade the quality of the that evaporating material. So that we can remove in case of CVD. Another important thing that I think Dr. Tanmay also discussed a lot, that using CVD you will get more conformal deposition compared to PVD. So you can see this kind of this uniform deposition in this kind of pattern substrate you can get using CVD, but in case of PVD it is very difficult where we have this line of sight deposition. So another few advantage are that there is no alloy fraction as it is there with the other thermal method. So these are the advantage of CVD. Now typical chemical reaction which is happening as I mentioned in case of silicon technology, we are using this CVD to develop this polysilicon, as a, let's say, gate material, as well as the silicon nitride as a typical insulator. So this is the typical reaction we are having when depositing this silicon or polysilicon, or as well as silicon nitride and silicon dioxide. So here basically this once again compound, some compound is decomposes to form thin film, or there is some reaction is happening and we are getting some deposition. So then these are how to what are the different types of CVD equipment we have in case of silicon technology. So these are the broadly two categories. So one is the LP CVD, another one is the PE CVD. So again, what are the advantages, disadvantages? So you can see quickly that in case of LP CVD we have good uniformity, but in case of PE CVD the process temperature is low. Now when we are saying that process temperature is low, do we really need to lower this process temperature? And if we really need to have any process temperature low, what is the reason behind this? So again, overall objective from industry point of view to develop any semiconductor technology, maximum performance at lower cost. Now when we will have some process equipment operating at high temperature, we need to put a lot of money, because at high temperature we need to supply a lot of power to our filament, so our electric bill will shoot up. So again, that is why in industry it has always been a motivation to develop our material at low temperature. So that we can get in case of PCVD, because in PCVD there is again names is plasma enhanced CVD. So this plasma is actually helping us to get the same quality of the material without going at higher temperature. So without getting like a higher electric bill, so we can still meet our requirement. So that is why this PCVD has another advantage compared to LPCVD or other high temperature process. So another important fact for this CVD, you can see this deposition rate. Deposition rate means how quickly we are depositing these atoms or layer on our silicon or any substrate. So here this deposition rate is limited by this reaction rate, and this reaction rate once again it is controlled by these two parameters, that is temperature and the pressure. So pressure inside the chamber and the temperature will decide the reaction rate, and which will eventually decide the deposition rate. So again, another fact that will decide this deposition rate is the arrival rate. So this arrival rate means arrival rate of atoms to your substrate. So that arrival rate also will be decided by the pressure inside the chamber. So again, you can guess if the chamber pressure is low, so quickly your atoms or gas molecules can arrive to your substrate, but for high pressure it is difficult. So these are the two parameters which will eventually decide our deposition rate for CVD in case of silicon technology. So this is how our LPCVD for silicon technology looks like. So these are the silicon wafers stacked vertically. So from here we are supplying this gas molecule. So inside this furnace we are having some reaction. Then we have some deposition like silicon dioxide or so. So then we have this exhaust. So some thing getting deposited on the wafer, and the byproduct is coming out on this track, through this track. So this is the typical schematic of LPCVD system for silicon technology, and this is the PECVD system. So again, this pinkish color, it is the plasma. So this plasma is again helping us to operate this chamber at lower temperature, still getting the same quality of material. So this is looks like something like this. So we have two electrode in between. We have this reaction happening under the plasma. And again, you will see probably, or you have seen this kind of system inside our clean room here. So this is the PECVD, and now second case study is considering the compound semiconductor, mainly the 3-5 semiconductor. So for your gallium nitride or gallium arsenide. So again, for this compound at a particular angle. So again, there is some computational like some CFD technique is also involved. So how to get the best deposition. So then you need to place that substrate in that way. So now this is the substrate. So here we will have some reaction metal organic compound along with arsenic phosphate like the gases, and then finally we have this exhaust system. So again, this arsenic phosphate, these gases, again silent, these are highly flammable gases, so we have to be very careful when we are using this emulsivity like technique. So safety is major concern in case of emulsivity, unlike other PVD technique. So then again, this is the again I was fortunate enough to use this emulsivity during my PhD time. So this is a typical arsenic system, arsenic phosphate based system. So here if we want to deposit gallium arsenide, so these are the two material or compounds. So arsenic along with the trimethyl gallium, so we'll get the gallium arsenide deposited, and then this methane will come out from the exhaust. So again, that is why this exhaust part also we need to take care properly. So we cannot simply let it go outside our lab. So we should have proper mechanism to treat this exhaust gas. So again, another few, these are the few dopants used for this compound semiconductor development using emulsivity. So this is the reactor. So inside this we have this reaction happening. So arsenic and this metal organic compound. And this is another this emulsivity I have seen in Taiwan. So this is the gallium nitride emulsivity setup. So this is the inside. So these are the different substrate placed, and we'll just cover this lid, and then we'll have the reaction. So from again similar type of configuration is also there for our PCVD setup here in our clean room. So then how the deposition is happening, so let us quickly see this using this animation. So initially this all the atoms are transported to the chamber, then some reaction is happening, then after reaction this absorption is going on. So in this after absorption we have different surface kinetics, and this surface kinetics is mainly decided by the temperature, growth temperature of the this reactor. After this surface kinetic, we will have this deposition, and then finally after this growth or the deposition we will have some atoms dissolve, and finally we need to evacuate those residue atoms. So this is how the atom by atoms deposition is going on inside a gallium nitride emulsivity. So again, this is some interesting fact. Again, as you know, this 2014 Nobel Prize was awarded to this scientist. He is Professor Nakamura. Now he is in UCSB. So actually, probably this was the first this Nobel Prize given for developing a process. So see, if you read these lines, so he used to work in a company. So again, there he got this emulsivity equipment, and his job was to build this gallium nitride, good quality gallium nitride. So again, you know, this Nobel Prize was awarded to invent the blue LED. So again, people knew that if we can get this gallium nitride very good quality, then we can get blue LED. But the difficulty was to get good quality gallium nitride material. So this Professor Nakamura, what was his job in that company? So he used to go for even for more than 1 year. So every day his job was to change in the morning, to change the configuration of this emulsivity, grow in the evening, and check the result after that. So for 1.5 years or so he did this rigorously. After that he developed this two-flow mechanism, and using this two-flow emulsivity technique he got very good quality gallium nitride layer, and then he could get the blue LED or blue light emitting from the device. So this was his contribution. Again, this whole story is very interesting. If you are interested, you can read this Nobel lecture. So this is the importance how the typical growth mechanism can also give us the Nobel Prize. So overall, then what are the advantages and disadvantages of this emulsivity like technique? So as we discussed, that we can get very good quality crystal. Then the growth rate is also high compared to the PVD technique. So then again, for the bulk production, So this is very good technique, emissivity, because the growth rate is high. So at one go we can develop or to grow or develop a typical device, less time is required. So from industry point of view, they will always look at the throughput. So then this emissivity technique is better compared to the PVD technique. So in case of compound semiconductor, the PVD technique was or is this your MB. So that is why industry prefer emissivity compared to MB. So again, but everything is not good for this emissivity also. So as we discussed, that it is difficult to achieve this precision if we deposit this very thin film or order of a few nanometer. So then another issue is with the safety because of the different precursor, toxic and flammable. Then again, this exhaust byproducts also should be taken care properly. So these are the few disadvantages. And okay, so just to comment when to use which technique. So this is final conclusion. So we should always know. So see, for this kind of compound semiconductor, when we are growing the thicker layer, we are using this emissivity, but when we are depositing this thin layer, we are using MB, because using MB like PVD technique, we can control the thickness at order of a few nanometer, which we cannot even in case of emissivity. So then your substrate grow next thick layer using emissivity, the top thin layer where your electron will flow, that is the active part of the device, grow that part using MB. So this is the best way to get the good high performance devices. So then quickly, if I go through this other compound semiconductor like gallium oxide, so then here we are using this LPCVD. So this is the typical schematic which we are using to develop this gallium oxide like compound semiconductor. And this is the workflow. So initially we load this sample, then vacuum, then argon purging, ramping, deposition, and then cooling. So this is how in case of gallium oxide deposition, we have two precursors, the gallium metal itself along with the oxygen. So and again we use this argon as carrier gas. So inside this is the reactor or the furnace, and inside this we have a board, and below the board we have this gallium metal, and the oxygen and argon gas is flowing inside the chamber, and under some high temperature around 850, so we are getting this gallium oxide deposited on the substrate. So this is the temperature profile what we are using when depositing this gallium oxide. So this is how this system looks like, and then we have done some characterization also after depositing this gallium oxide. So again we confirm so that we are getting very good crystalline quality gallium oxide using this LPCVD technique. So from this XRD, so we can confirm this. And then another important parameter to look at after depositing material or developing material is the surface smoothness, because if the surface is rough, then after metallization, because overall our objective, let's say if we want to fabricate the transistor, so this gallium oxide on top, we need to deposit three metal, source, gate, drain. So if the surface is very rough, so the interface between your metal and the semiconductor will not be very good. So then it will not get good device performance. So that is why surface roughness is another thing we should optimize after confirming the crystalline quality of the material. So then again we studied how the gallium metal, that is the gallium, that is a precursor. So how this gallium metal is deciding the surface morphology. So again you can see this when we are increasing this gallium metal inside the reactor. So this surface roughness is changing. And finally, when we increase this gallium metal very much, so like from 2 milligram to 25 milligram, 40 milligram, or 80 milligram, we were not getting any thin film at all. Some nanostructure is all forming. So that is why from here also we can conclude that this precursor, amount of precursor, also decide your surface, or not only the surface roughness, complete morphology also will be decided by the precursor. So here higher amount of gallium is not giving you some thin film. That means if you take the higher gallium, so you will not be able to make any transistor or electronic devices out of this kind of morphology or this kind of nanostructure. So this is the take-home message. So this precursor is very important. Then again we have seen that if there is a crystalline or crystallinity difference when we are changing the gallium, so you can see this gallium G2 means when we are taking the 2 milligram of gallium inside the chamber, so then this is the 5 milligram of gallium. So when we see this crystallinity, there was as such no change, only the change was when we took very high amount of gallium. So there were a few other peaks are coming in XRD. So then again, so from surface morphology point of view also, this is not a workable material for electronic device. So then this is the UV spectroscopy. Here we confirm the band gap of this material. Again, this band gap of this material is very high compared to the normal silicon. So this is UV visible spectroscopy. From here we can calculate the band gap, and the band gap of this material was above 4.5 electron volt. Again, we know that for our silicon it is 1.1. So this gallium oxide like material has very high band gap, and that is why this is suitable for high voltage or high power application. So that is why I told initially when I showed that how the material evolved considering the power application, and why we are working towards this wide band gap semiconductor for high power application. So then again, this is another characteristics like how the band gap is changing with the gallium concentration, and importantly considering the CVD this context, so how the growth is happening. So here we are taking this sapphire as substrate. So then on sapphire we are our two precursors are gallium metal itself and then oxygen. So then initially we are getting this alloy. So this 4 gallium then oxygen, we are getting Ga2O. So after this oxidization of this Ga2O with more oxygen, it is converted in Ga2O3. So our ultimate objective was to get Ga2O3. So now let's see in what is happening, how our morphology is changing. So this is kind of postulation. So to understand why this morphology is changing with the more and more gallium. So then initially, so this kind of island is forming that using this alloy. Again, finally, this when we will deposit, so we will get this coalescence of this all island, and finally it will give us this kind of thin film of gallium oxide. So typically this mechanism is called SK growth or Transky Krasnov growth. So after some Russian scientist name. So this is called island plus island growth. So in those who are in this epitaxial growth, they know. So there might be island plus island plus thin layer. So all thin on thin layer. So this kind of different growth mechanisms are there. So but here it is typical island, and these islands are merging, and we are getting this thin film. So and again there are few gas-based reaction also happening, and that is why we are getting this vapor solid growth, and which is leading to this nano rods, which is undesired. So we should be able to control this pressure as well as this oxygen precursor and gallium precursor. Then we can control whether we'll get the nano structure like this morphology or we'll get the thin film like morphology. So this is the main take-home message. So how this precursor control can lead to different type of morphology of for growing semiconductor. So then another thing was how to dope this material. So because as I just mentioned, this gallium oxide has very wide band gap. So again we know typically our insulator has also very wide band gap. So don't you think this then gallium oxide, how can you use as semiconducting material? So yes. I think 15 years back or so, people use this gallium oxide like wide band gap semiconductor as an insulator. But very recently, they could dope this semiconductor. Again, this is irrespective of any gallium oxide or any compound or any other semiconductor. As we can dope this semiconductor, we can change the conductivity of our material, and as we can change the conductivity of material, we can make devices out of it. So this is the main objective. to select any material for devices, because in devices we know basically apply some voltage, get some current, and that current we should be able to control. This is very in brief from device point of view, the expectation from the material. Now in case of material, the conductivity we should be able to modulate or control, and that conductivity modulation all is possible if we can dope this. And that is why in case of gallium oxide also you can see, so it has very wide band gap, so it will take a lot of energy to take one electron from the valence band to conduction band. So then you cannot use this this gallium oxide without doping. Again we also faced a lot of difficulty to get any current out of these devices initially. Then we tried to dope this gallium oxide using tin. So tin act here as dopant. When you used tin, so then we saw again there was some challenge, because tin has different vapor pressure. So incorporating tin in thin film gallium oxide was very difficult. So every time we are getting some nanostructure, and that was not our objective. Our objective was to get the thin film. Now how to get thin film of gallium oxide after incorporating tin as dopant? So this was initially very difficult. You can see initially we got some nanostructure, and just because this is some research we did. So here you can see we also observed some shift in the XRD. What does this mean? Shift in the XRD means we formed alloy. Alloy means now we are getting probably SN gallium oxygen. So our objective was to dope this. And what is doping? So doping is, again in case of silicon, if you know there is some figure 10 to the power 16 centimeter number of dopant per centimeter cube. So typically how many atoms are there in silicon or any semiconductor? Typically it is 10 to the power 22 number of atoms per centimeter cube. And if our doping level is 10 to the power 16 or 17, you can understand out of every 10,000 atoms you will find only one dopant atom. Out of every 10,000 atoms you will find let's say 10,000 silicon atom, there will be one arsenic atom. Then only you can call this as N-type silicon. So doping is different and alloying is different. So here we formed alloy. So that means all this atomic share is become equal. So that was also not our objective. So that is why we observe this peak shift in the XRD. So we incorporated more tin that we desired initially. So again we tried to control this incorporation of tin. So how can we reduce the tin incorporation in the gallium oxide so that we can change in the conductivity but no change in the crystallinity or no change in the XRD result. So after doing lot of iteration, so finally we found that this is the, again this is the job of a grower.